In this video, I'm going to walk you through the details of all the different ports that you can use in your AT Robots assembly program to talk to external devices that are connected to them. And when we look at that, we care about not only what varieties of devices we have to take advantage of, but we need to know whether they're input or output or both. And we need to know the time associated with them, as well as what kind of arguments we need to use to interact with them appropriately. So there are two slides related to ports, and we'll go over those now. The first port listed here is the speedometer port. If you look at it, you can see it's an input port, so it's something you can get data from, but if you write to it, nothing happens. And most of the ports on this page are input ports. You'll also notice that quite a few of the first ports have a time associated with them of 0 cycles. That doesn't mean they're free to use, because when you use the IPO instruction, the input from a port instruction, to talk to one of these ports that takes 0 cycles, the IPO instruction already consumes 4 clock cycles. So you at least spend 4 clock cycles whenever you use one of these ports. So the first of these, and it's an input port, is the speedometer port. It'll tell you your current throttle setting between -75 for going in reverse to +100 for full speed ahead. There's a heat sensor that will return your heat level between 0 and 500. And somewhere up in there, I can't remember if it's 300 or 350, maybe it's 400. I don't recall, but somewhere in there, if you get your heat to that level, your robot will fundamentally just stop where it is on the arena floor and be a sitting duck until your heat goes down to a point where the program can pick back up running again. There's a compass port, which returns the current heading of the robot. Remember that in AT robots, directions are based on a 256-degree circle, and 0 degrees is due north of your screen. So when you get your current robot's heading, it'll be a number between 0 and 255. You can also get the offset of the turret through the first turret sensor port. Both turret sensor ports have the same name, at least as they're listed here, but there are predefined constants that refer to their numbers. So this is really, the first one is really port number 4, and the second one is port number 5. What distinguishes them is that the first one returns the current turret's offset. That means if your robot's facing this direction and the turret's facing about this direction, you would know that the turret is offset about 192 degrees. That's all the way around like this, 3 times 45 in the human world, but 192 in the AT robot world. The second one doesn't tell you the offset of the turret relative to the robot. The second one of the turret sensor ports tells you what angle the turret is facing in the global arena compass. So they are two different concepts. There's a damage sensor, which returns what your armor level is, and that's a value between 0% and 100%. Although you should never get 0, because you'd already be dead if your armor gets to 0. There is a scanner port also for input. This is when your robot shoots out that gray triangular pie piece. So when you input from the scanner port, you show that little pie piece, and whatever robots are within that pie area, the closest one of those, assuming that there is one, will have its distance from you returned by this port operation. But that activity actually has a second thing that happens. So if you do a scan for another robot and you actually find a robot within that scan arc, then you can use the accuracy port to find out sort of about how far off from the center in either direction this thing is. When you get the accuracy value back, it's a number between -2 and +2. So effectively that means the scan is broke up into these regions centered about my fingers as an example. So region 0 is dead center of the turret with some amount of leeway depending on how wide your scanner is at this particular moment in time. But you've got 0 degrees, -1, or 0 accuracy, -1 accuracy, -2 accuracy, 0 accuracy, positive 1, +2. Oh, I'm realizing that's from my view and not yours. So -1, -2, +1, +2. Maybe in post I'll flip my picture around suddenly to make that all make sense. So your scan arc, the total width of it, regardless of whether it's skinny or wide, is broken up into 5 regions. And all you get is information about which of those 5 regions the closest robot you last scanned was in. That means you got to do a little extra work than just scanning and finding somebody before you can really start shooting very accurately at them. There is a radar port. The radar port is a little bit expensive. It takes 3 clock cycles on top of the 4 cycles for the port instruction. But it tells you the range to the nearest target, so the distance to the nearest target, not its direction or the angle that you have to turn to point at it, just how far away the nearest other robot is, the closest robot. Then there's a random number generator. When you get the random number generated, you get a random 16-bit pattern. So it's unlike the rand function in C and C++, which only gives positive numbers. This one just gives you a random bit pattern that's 16 bits long. There's the throttle port. Notice now we've switched from input to output. This is output only. If you want to know the current speed, you have to use the speedometer port for input. So you output to the throttle a number between -75 and 100, and that indicates how fast you want to go. 100 positive means 100% speed in the forward direction. -50 means 50% of your speed in the reverse direction. Right? So you can go backwards or forwards, but you can't go backwards as fast as you can go forward. You can output to the rotate turret port. This will offset the turret from its current value. So if robot's facing this direction and the turret's facing this way, and then you say, so this is about 32 degrees in robot land. If you say turn, offset the turret, rotate the turret 32 degrees, that's a clockwise number because it's positive, so it's going to go from here to here. If you say to go 32 degrees a second time, that would obviously take it from here to there. But if you're over here and the turret starts rotating 32, but you tell it to go 32 again before it's done, this is a cumulative rotation. So it's not going to go 32 additional degrees from here. It's going to go your original 32 plus a second 32. So that's a cumulative rotation. You can also aim the turret to a specific offset value relative to the robot itself. So somewhere between 0 and 255 degrees offset from the robot's current direction. There's another port for steering, one of the most common ones. Turn the robot this many degrees. And so it does that relatively abruptly. The smaller the number of degrees you want to turn, the fewer cycles it takes to get it done. That's something to be aware of, because very often a robot will get bumped against the wall and it will try to turn away from the wall and then drive. But the person who codes it will tell them to, steer, I don't know, let's say 64 degrees, which is like 45-degree angle. So it wants to go from here to here, and then they intend to drive away by outputting to the throttle port 100, so drive away. But what will happen is they'll hit the wall, stop, they'll start to turn their 64 degrees, but it only takes the CPU moments to have executed that instruction, even though the hardware hasn't caught up yet. The robot hasn't finished turning. Then you'll suddenly run the output to the throttle port, go full speed ahead, and the robot will just drive back into the wall. It'll finish steering at that point, but it won't drive away because it already tried to drive and got stuck. So one of the fun aspects of this whole thing is having to think through the fact that sometimes you're asking the robot to talk to a hardware device and do something, and the instruction that asked it to will be long done and moved on before that hardware has had the potential to catch up. So you'll learn as we go through these videos that we have to figure out whether these things are done or figure out a way to give them ample time to finish so that we don't screw up what we intended. So that's steering. Steering is also a cumulative operation, although it isn't noted here. The weapon port, whenever you output to it, it shoots off your laser, but you can offset that by -4 degrees from center, or all the way up to +4 degrees from center. That way you don't have to spend extra instructions rotating the turret to shoot off to the side a little bit, and that's very useful. There's an input port for sonar, and it returns the heading, the actual angle, to the nearest target between 0 and 255 degrees. I can't recall off the top of my head whether that heading is relative to your robot's current heading or relative to the center of your robot. So you could have a robot facing this way, and its center is here, and another robot over here, which is 192 degrees away from north. If we're just thinking about the center of the robot, it's going this way, right? And that's one possibility. The other possibility is it's how many degrees you have to turn your robot to make it face the center or the other. There's only really a couple ways to find out. One would be to pore through the massive AT Robots documentation, probably a sensible thing to do. Find the answer and hope that it isn't misdocumented. Another would be to look at the code that implements those instructions, but that's a little bit complicated too. But possibly the easiest thing to do is set yourself up a really simple program where you have a robot utilize this particular port and then output the value that it gets from it using the error instruction, which prints it up in your little status area. So you can see what the value is, scratch your chin and say, oh, I understand what that number is now. Right? So we do that a lot in the real world, write very simple programs just to figure out how things actually work. So maybe we'll do that for sonar, but note that the sonar takes 40 cycles. Now that's presumably because of all the fancy trigonometry that must be done to calculate angles or something. But it definitely means that this is an expensive instruction and should be used sparingly. Excuse me. The scan arc instructions for both input and output. It allows us to, if we're using it as output, to set how wide our scanner arc is, so we can make it skinnier or wider. And we can send it numbers between 0 and 64. Remember that 64 degrees in the AT robot world is 90 degrees in the human world, right? It's a right angle. And the way this particular value works is whether you're sending it to the scan arc to set a new arc width, or you're reading it to find out what your current arc width is. Remember that the arc width value here, the scan arc, is, let's say I set it to 32. That means I'm going to go 32 degrees off from center in one direction and 32 degrees off center in the other direction for a total of 64 degrees wide. So you double the number. If you send a 64, that really means it's 128 degrees wide, which is 180 degrees in the human world. Overburn, everybody's favorite to play with, and it's like playing with fire. Because it literally soups up your engine speed. It soups up the weapon speed. The weapons fly faster. They cause more damage. They even get colored yellow instead of white. But they generate significantly more heat. And it doesn't take that many overburn shots in a row with no other code to bring your heat up so high so quickly that you self-destruct. So be careful with the overburn. If you use it for output, you're basically telling it to turn on or off. So if you send a 0 to this port, you're turning Overburn off. If you send anything else, you're turning it on. You can find out whether it's on or off by using it as input. By default, it is off. The wireless transponder port allows you to do some wireless communications. So you put a number that's going to represent your ID to be sent across the world. There is a shutdown level port. I cannot recall for the life of me while I'm recording this what that is. I have not personally used it or haven't used it for more than a decade, so I don't know what it is off the top of my head. I'll have to look it up. You can look it up. The COM channel level, or COM channel port allows you to set which communication channel you're going to talk on for your wireless communications with the transponder. The mine layer allows you to lay mines or find out how many mines you have left out there. So if you output to this drops a mine. I'm going to refer you to the documentation because I didn't make an annotation here on the slide. But when you output to the mine layer, by default, it's going to drop a mine so that it is hyper insensitive, meaning that another robot is going to have to drive over the absolute dead center of that mine to make it explode. This port actually takes a value, and the value you send to it is the sensitivity. You can either experiment with that and see what big numbers or low numbers do, or you can look that right up in the atr2.doc documentation file, and it has descriptions of it. A mine trigger port allows you to find out how many mines you've previously placed, and it allows you to detonate the mines that you have put down remotely. So this is sometimes used by robots who detect that their armor level is getting very low and so they're about to die. And in hopes of getting a kill through collateral damage, they remotely trigger all their mines and a beautiful display of fireworks on screen. And the little circles that come out of them are sort of the damage rings. And if another robot is near enough, it may receive damage that hurts it, maybe decreasing its rankings overall in the tournaments, or maybe it even is the last straw that kills that, and then the robot who remotely detonated its mines will get credit for the kill. The last port to mention here is the shield port. So if you've beefed up your shield configuration points so that you actually have a shield on at all, you can use this port to turn the shield on or off, or find out whether or not it is on or off. Now for each of the ports on these two pages, starting with port 1 all the way through port 24, the way we identify the ports is by providing one of these numbers. However, nobody wants to remember that if you're going to steer, you have to use port 14. So for each of these, I'm going to slide down to the bottom of this slideshow. For each of these, there are predefined constants. So we know 14 is the steering port because we saw it on the previous slide. If you jump down to these last two slides of constants, you'll see, well, there's the value 14, and that's the same as the number for the jump greater than instruction, and the same for the P steering constant that's predefined, as well as an interrupt, the transmit interrupt. So everything in this row, each of those strings is equivalent to the number 14, and they can all be interchanged. Instead of doing jump greater than, you could write where your instruction mnemonic should be P underscore steering, and it'll effectively do a conditional jump if the greater than flag is set. But this means I can say IPO tab P underscore steering, and my code is much more readable. Read in from the steering port into register, whatever, that kind of thing. And so it makes it very nice. Well, that's it for the ports. Don't forget that as you're looking at those ports to consider how expensive they are in terms of clock cycles, and try not to use their port numbers directly as a number of the oldest example robots do. Instead, go to the constants table, to find out the identifier that you can use instead. And pretty soon you'll memorize the main ones: throttling, throttle, setting the scan arc, doing a scan, shooting the weapon, or manipulating the turret, right? And steering. Those are like the main ones that are used all over the place. So once you get the hang of those, you'll be writing great robots in no time.